Welcome to our channel, Mootechie. This presentation will guide you through one of the foundational concepts in microbiology, the bacterial growth curve, which helps us understand how bacterial populations behave over time. Introduction. What is a bacterial growth curve? It represents the population dynamics of bacteria over time in a closed batch culture system. This means we are observing how a group of bacteria changes when placed in a fixed environment with limited resources. It is divided into four distinct phases: lag, log, stationary, and death. Each phase describes a different stage in the life of the bacterial population. It is quantified by measuring optical density, often at OD 600, or by counting viable colony forming units, known as CFU. These are the two most common ways to track how many cells are present and how they are growing. Understanding this curve is crucial for calculating generation time, testing antibiotics, and optimizing bioprocesses. In essence, it's a vital tool for both research and industrial applications. The diagram here shows a typical growth curve. On the vertical axis, we have the number of cells on a log scale, which allows us to see large changes clearly. On the horizontal axis, we have time. The curve begins with a flat lag phase, rises steeply during the log or exponential phase, levels off in the stationary phase, and finally declines in the death phase. It's a visual summary of the entire life cycle we'll explore. Bacterial growth curve, lag phase. Lag phase, preparation and acclimatization. Metabolic activity increases significantly as cells synthesize enzymes, RNA, and proteins. Even though the cells aren't dividing yet, they are very busy internally, preparing the machinery needed for reproduction. There is no immediate increase in cell number. The population size remains essentially constant. So, if you were counting cells, you wouldn't see a rise during this initial period. The cells are repairing damage and adjusting to new environmental conditions, like pH, temperature, and nutrient availability. Think of this as the bacteria getting used to their new home before they start a family. The duration of this phase depends on factors like inoculum size, the age of the cells used to start the culture, and differences in media composition. A larger and healthier inoculum might shorten the lag time. The image labeled lag phase adaptation period visually represents this phase with a timeline from 1 to 5, showing a flat line indicating that while time passes, the cell count hasn't begun its rapid increase yet. Now, let's move on to the period of rapid expansion. This graph is titled Log of Cell Number Against Time, and the highlighted section is labeled Exponential Phase, Rapid Cell Multiplication. The line curves upward sharply, indicating the fast growth we are about to discuss. Log phase, exponential growth. During the log phase, cells divide by binary fission at a constant specific growth rate, represented by the Greek letter mu. This means each cell splits into two at a predictable and steady pace. The population doubles at regular intervals, a period known as the generation time. This is when the bacteria are multiplying at their maximum possible speed under the given conditions. Metabolic activity reaches its peak and the cells are most uniform in their properties during this period. They are essentially identical highly active little factories. This is also when the population is most sensitive to antibiotics and environmental disruptions. Because they are growing so rapidly, interventions can have the greatest impact. As resources begin to run out, growth inevitably slows. Stationary phase, growth equals death. Phase 3, stationary phase, nutrient depletion and equilibrium. Population growth stabilizes as nutrient levels become limiting and waste products accumulate. The environment can no longer support unchecked growth. The rate of cell division equals the rate of death, resulting in a constant viable cell count. The total number of living cells plateaus, creating a flat line on the graph. To survive this stressful period, cells undergo morphological changes such as becoming smaller or developing thicker cell walls. These adaptations help them endure the harsh conditions. Production of secondary metabolites like many antibiotics often occurs during this phase. When growth stops, bacteria often switch to producing these complex compounds. Eventually, the environment becomes too toxic to sustain the population. Death phase, decreasing viable cell count. Death phase, population decline. Death phase, decline and lysis. The viable cell count decreases exponentially as the rate of death exceeds the rate of growth. The line on the graph now slopes steadily downward. This decline is caused by the severe depletion of essential nutrients and the accumulation of toxic waste products. The culture has essentially poisoned itself. Cells may undergo lysis, bursting open or assume abnormal shapes due to structural damage. The integrity of the cells break down. Some surviving cells may form durable spores or enter a viable but non-culturable state known as VBNC as a last-ditch effort to survive until conditions improve. Let's summarize the entire journey. Summary: Growth curve overview. The curve is divided into lag, log, stationary, and death. First, the lag phase. This is the adaptation period where there is no net increase in cell numbers. The bacteria are preparing for growth. Second, the log phase. This is the period of exponential growth where the population experiences its maximum division rate. Third, the stationary phase. Here the growth rate equals the death rate due to nutrient depletion. It's a dynamic balance. Fourth, the death phase. This final phase sees a decline in viable cells due to the accumulation of toxins and lack of food. The slide also shows key formulas. Doubling time G, calculated as time divided by number of generations, growth rate mu, calculated as the natural log of final population minus the natural log of initial population, all divided by time, and yield Y, which relates the change in cell mass to the change in substrate consumed. These formulas allow us to quantify the dynamics we've just observed. Thank you. We hope you enjoyed this journey through bacterial growth dynamics. Questions? Share your thoughts in the comments below. Don't miss out. Subscribe to Mootechie for more bioscience content.